Okay, this is David Zierler, director of the Caltech Heritage Project. It's Thursday, January 20th, 2022. I'm delighted to be back with Professor Alexei Kitaev. Alexei, it's great to be with you again.
Thank you.
Alexei, in our first conversation, we did a very interesting and wonderful tour of your approach to science and the research. Now I'd like to go all the way back to the beginning and learn about your family origins in Russia. Let's start with your parents. Tell me a little bit about them.
Uh, my parents lived in Voronezh. It's a town where I was born. It's actually a pretty big city now, about 1 million people. But they were born in different places. And my father was born in a little town in central Russia, and my mother was born in a little town in Ukraine. But that was not because she was Ukrainian. She was traveling with her father, who was in military service, and they lived in various places.
Alexei, what were your parents' experiences during World War II?
Um, uh, they okay. My mother lived in a evacuation with her mother in Orenburg. It's a city a little east of Moscow. Well, actually, pretty far east. But it was hard. It was cold and shortage of food. And during that time, my grandfather, my mother's father, was fighting in the war. And my father's parents were doctors, and they were both doctors, and they worked at a hospital during the war. And I don't remember where it was. They were traveling. I guess they were moving from place to place. But right now, I cannot remember the details.
Did your father serve in the military during World War II?
Oh, he was young for that. Only my grandparents served in the military. As I say, my father's parents were doctors, so they served as doctors. And my mother's father served as a pilot. Actually, he was a navigator on a military plane.
What were your parents' professions? What did they do for a living?
My father has died, unfortunately, but he used to be a physicist also, an applied physicist. He was working at Voronezh University, doing some applied physics and engineering, and teaching students also.
What kind of physics did he do?
He started with some radio communications, but I remember what he was doing in the last, say, 20 years of his life. It was acousto-optics.
And what about your mom? Did she work outside the home?
Yeah, she also worked at the university for some time, and then she moved to a different place, and she was doing some engineering job, but not very high level. And she tried to spend as much time as possible with us, with me and my brother.
Alexei, did you see what your father did? Did he take you into work? Did you know what it meant to be a professor of physics when you were a boy?
Oh yeah, yeah. That was very interesting. That was a great experience. When I was a little boy, my parents would take me to the university, to my father's lab, and I was allowed to play with some equipment. Basically, I was playing with an oscilloscope and looking at the patterns. I could produce the Lissajous patterns, and that was fun.
Did your father ever talk about politics or about the role of the Communist Party in science?
No. Yeah, and as you can imagine, people's view of politics would be completely different than in the US. And you can also imagine that in the US, different people's view are also different. So, but he didn't talk about politics very much.
Alexei, you would have been very young, but do you remember the space race between the Americans and the Soviets?
Yeah. Well, I guess the time I remember was when the US was launching spaceships to the moon. And I remember that there were news that a spaceship orbited the moon and then landed with people on the moon. That was when I was a little child.
Were you always interested in math and science?
Yeah. Actually, that experience of playing with some physics equipment made a great impression on me. I loved science. And I also loved math. So first I thought I would become a mathematician because I didn't know much of physics. But then I was always in the middle, and at some point, due to some circumstances, I became a physicist.
Alexei, tell me about your first school, your elementary school. Was it a big school or a small school?
It was a big school. I mean, it wasn't divided into elementary, middle, and high. It was a 10th grade school, and the education was 10 grades at the time I was in school.
And looking back, was it a strong curriculum in math and science? You got a good education?
Yeah. It was a very reasonable curriculum. And in high school, it was specialized in math. And I'm not sure if you know this, in the Soviet Union, there was a system of specialized schools. Actually, they were specializing either in math or in foreign languages. And in math, it would mean that we would have maybe twice as many math classes as in an ordinary school. And such schools existed in all large cities around Russia. And I asked some of my colleagues later when I was at the Landau Institute, they all went to such schools. So it was a very efficient system to prepare people to work as scientists and engineers.
Alexei, did you do very well in school in math and physics? Were you near the top of your class?
Yes, I did.
Now, when you were a teenager, when the Russians were in Afghanistan, was serving in the military or being drafted, was that something that you needed to deal with?
Oh, well, that was a concern. It was actually, at the time, I was going to the university, and if I failed to be admitted to university, I would have been drafted. But that didn't happen.
What is the process like of choosing a university in the Soviet Union? What options do you have?
We didn't have an application system where you could apply to multiple universities. You had to choose which one you're applying and go there and submit your documents and take tests. And when I decided to go to the Moscow Institute of Physics and Technology, and there were two written tests in physics and in math, and two oral tests in both subjects. And there was also an essay, but that was waived because I received the top grades on the first four tests. And also I was, it's called gold medal in school, meaning that I was excellent in grade school. So they waived the last test.
Alexei, what year was it when you arrived at the Moscow Institute?
It was 1980.
And I'm curious at this point how much you thought about the Cold War, or as becoming a scientist, if you saw yourself as working on behalf of the Soviet Union and what it represented.
So I'm not sure.
Did you feel insulated from those things?
I also didn't think much about politics. Of course, I was indoctrinated like many other people in the Soviet Union. But on the other hand, I just wanted to stay away from politics and just do science. I thought that science was useful, of course, and I could do something good, but I was just focusing on the work.
Did you recognize that even just wanting to do science, that in the Soviet Union there were limitations placed on scientists by the government?
Well, actually, science was one of the few things where you could be relatively free from pressure, from political pressure. I mean, natural sciences like physics, mathematics, chemistry, biology. And that was an advantage of doing science.
Alexei, was the Moscow Institute focused exclusively on science and technology, or they offered humanities as well?
No, that institute focused exclusively on science, physics and applied mathematics.
And at that point, did you think you would focus on mathematics initially?
It's tricky because I first entered the program in applied mathematics, and I was kind of confused because it's called mathematical physics, and I thought I would be doing basically what's called mathematical physics now, meaning applying, doing some high-level math and connecting it to physics. But in reality, turned out to be solving PDEs on a computer. That was called mathematical physics. I mean, they named the program like that, but in reality, it was focused on solving equations on a computer.
What computers did you have in those early days? What were you working with?
Well, first, I didn't stay at that program very long. And second, the computers that we had access to in the first couple of years of the university was a very old machine. I'll say in Russian, Besam 6. It's some abbreviation. It's a computer which was in the first year at least. Then they changed this. It was controlled by punch cards. So you need to write your code and submit it to some place where some person would type the code and produce the punch cards. And then you would run your program. But of course, during the time when I studied, they improved it a little bit. But basically, those computers were pretty outdated even for that time.
Alexei, had you ever been to Moscow before? What were your impressions when you first arrived?
I had been in Moscow, just visiting. And of course, when I arrived and had a chance to stay in Moscow, actually, the institute was outside Moscow in a suburb. I would need to take a train to Moscow. But anyway, it was fun to work there and go to different places like museums, theaters. So it was very interesting.
How big a school is the Institute? I mean, is it like an MIT? Is it a very large program?
I think it's smaller than MIT, but bigger than Caltech.
Uh-huh.
And I'm trying to count how many people were there. One department, one class had 100 plus something people, and there were several departments. So about 700 students times 6, because there is 6 years of study. So it make between 4,000 and 5,000.
Now, after your initial foray into mathematical physics, what program did you settle on?
I switched to theoretical physics at the third year, and there was actually an exam. I needed to take an exam to enter this group, and I started doing theoretical physics from year 4.
This was more comfortable for you. You felt more at home in theoretical physics.
Yeah. Actually, I didn't pass this exam from the first time. The first time I failed, but eventually I succeeded.
What was interesting to you most when you first got involved in theoretical physics? What were you working on?
This group, it was Garkov's group, Lev Garkov's group, was specialized on condensed matter. And at the Landau Institute, there were faculty doing all kinds of theoretical physics. And so there were some students doing different things, but most of the students were specialized in condensed matter physics. And I also worked in condensed matter. When I decided to go there and to take the test, I read something about condensed matter physics, and I was excited. In particular, I read Anderson's paper, or Nobel lecture. I think it was a paper explaining the results for which he got the Nobel Prize, and it was about spin impurities in metals. And it was fascinating because he proposed a simple model which explained some experimental facts. And this way of thinking, just inventing models that don't have to be very, very complicated, but they must capture some essential thing of the physical system. That aspect fascinated me. And actually, throughout my career, I was focusing on inventing simple models.
Now, I'm not sure how the names translate in Russian, but around this time, there was the switch in the United States from the term solid-state physics to condensed matter physics. Was there a similar transition in the use of terms in Russia?
It was called solid-state physics, actually.
Now, did you stay at the Institute for graduate school, or how did that work?
Yes, I stayed in the Institute. Not exactly. Let me explain some details which may sound unusual because it was a unique system. At the Moscow Institute of Physics and Technology, they provided general education, mainly in the first 3 years. And then more specialized education in various fields of physics and sometimes applied mathematics. And those courses were offered at research institutes. So people working at research institutes in Moscow and the suburbs had a dual affiliation in their lab and at the Moscow Institute of Physics and Technology. And they were teaching students, either giving courses or doing lab works at those research institutes. So I was taking advanced classes at the Landau Institute of Theoretical Physics for the last 3 years of my study. And then I switched to the graduate school at the Landau Institute.
Tell me about the Landau Institute. What was it known for?
It's an institute of theoretical physics. It was named after Landau, but it was established by Landau students, including Khalatnikov, who was the first and long-time director of the institute, Gerkov, Zelashinsky, and others. And it was a great place for theoretical physics. At the time I came, there were about 80 physicists doing completely different things. And if you had a question in theoretical physics, practically in any area of theoretical physics, you could find an expert to talk with.
Alexei, how international was the Landau Institute? Were the professors traveling abroad? Would there be visitors from other countries that came to the Landau Institute?
Yes, they traveled abroad. In the Soviet Union, traveling was rather difficult, but they still traveled and they had visitors. And I came there, if I remember, the first time was in 1984. I came as a student. And during the initial years, when it was still Soviet Union, the traveling was limited, but we still had some foreign visitors who would give talks, and that was great. Later on, many people went abroad and just stayed there. And after that, the Landau Institute was not so great anymore. And that happened in early 90s.
Who was your advisor at the Landau Institute?
Valerie Pacrosti.
And what did Valerie work on?
At the time, he worked on the fractional quantum Hall effect. At least that was the topic I was trying to work with him together. But somehow it didn't work for me. I eventually did something completely different. But he was working, he's known for his work on phase transitions. And he also was doing some work related to phase transitions, even at that time.
And what about for you? What did you want to focus on? What was interesting for your thesis research?
I found a topic on which I worked with two of my fellow students, two of my friends, Leonid Levitov and Pasha Kalugin. And the topic is called Quasi Crystals. We were lucky that as students, we were learning in commensurate systems. And in particular, actually, let me explain what quasi crystals are and how we learned about them and how it's related to incommensurate systems. Crystals are periodic arrays of atoms, and a periodic array of atoms can have certain symmetries, like cubic symmetry, but they cannot have, for example, icosahedral symmetry. And it's easy to understand in plane. You cannot have a periodic lattice with a symmetry axis of order 5. You can, for example, you cannot pack pentagons in a regular periodic pattern, but that is a special case. I'm saying some mathematical fact that there is no lattice with a pentagonal symmetry. And of course, that means that there are no crystals with pentagonal or icosahedral symmetry. And in 1984, there was a discovery. People saw crystals, or the structure was actually unknown, something that looked like a crystal with an icosahedral symmetry. The diffraction, the X-ray diffraction pattern, actually it started with electron diffraction pattern, I think. The electron diffraction pattern showed Bragg peaks like a crystal, but they had clear pentagonal symmetry. And that was done by Sheckman, Black, Gretius, Kahn, experimentalists. And we saw this paper, and we came out with an explanation that it's a sort of incommensurate structure, because the problem with icosahedral symmetry is that it's not possible to have only three periods, like in the x, y, and z axis with an icosahedral symmetry. But it is possible to have six independent periodic patterns, six periods. And that means that the structure can be pictured as a periodic lattice in 6 dimensions, and then restricted to a 3-dimensional space. So secretly, it's 6-dimensional. So that was our first paper on quasi crystals, and we studied quasi crystals for several years, and I did my PhD on that subject.
Now, were you aware of Paul Steinhardt's research? Was he working on quasi crystals at this point?
Yes, he did, and we read his paper. First, we came up with our explanation. Then we saw his paper with Levin, and his explanation was better in the sense that there was a geometric explanation. Basically, it was based on Penrose tiling, and in Penrose tiling, you can force this quasi-periodic order using microscopic constraints. In our explanation was using an effective free energy. But for metals, actually, our explanation works well because interactions in metals are not short range. So I still don't know which explanation is better.
Alexei, as a graduate student, were you allowed to travel abroad? Could you go to international conferences?
Oh, excuse me. Maybe I need to move to a different place because it's too noisy here.
Sure.
Oh, actually, I think now it's okay.
Yeah, it's fine. It's fine.
Doing some work outside. So, as a graduate student, I could actually travel, and that was a beginning change in the last years of the Soviet Union. It was nice. I went to Trieste to attend a conference on quasi crystals, and I also went to some other places. Still as a graduate student.
Was your thesis research on quasi-crystals, was it connected to condensed matter experimental physics at all, or observation in any way?
Physics, well, of course it's condensed matter. And as I say, our work was related to an observation, to this experiment by Sheckman Black-Gratis Cam. We explained the structure of a quasi-crystal. It wasn't very closely connected to experiment because it's a kind of general explanation.
What does the term quasi mean? Why a quasi-crystal?
Because it has some periodicity, but it's not exactly periodic. There is a definition of a crystal. A crystal is some pattern that has the translational symmetry. In 3 dimensions, it's 3 independent translations. A quasi-crystal doesn't have a translational symmetry, but it still has some periodic motifs, which are seen in diffraction patterns.
Alexei, to foreshadow a little bit, in graduate school, do you see intellectual origins that would lead to your interests in quantum information? Is there a natural intellectual connection that got you from condensed matter theory to what would become to be known as quantum information?
There is no natural connection with condensed matter, but there was something that sparked my interest in quantum computation, and it happened very early while I was still an undergraduate.
Oh.
I read a book by Yuri Manin, Computable and Uncomputable. The book is on mathematical logic, but it had an introduction where Manin tried to come up with some examples where logic could be useful, and it's not trivial to come up with some example with such examples, because logic is a very abstract subject. And one idea was that quantum mechanics is difficult simulating quantum mechanics is computationally difficult. And Manin thought that that might be an indication that quantum mechanics itself can work as a powerful computing system. There were just two paragraphs in the introduction that caught my attention, and it was an expression of this idea.
Why did that catch your attention? What was so interesting to you about this?
Well, I realized it was a great idea. I didn't know whether it was novel or not, but it was really great because first, quantum mechanics was mysterious to me. It was maybe during my second year in college, when I didn't know enough quantum mechanics, I started reading Feynman's lectures, and Feynman had some elementary topics in quantum mechanics in his lectures. And I hadn't studied quantum mechanics seriously at that time. So it was kind of mysterious and fascinating subject. And then I learned that quantum mechanics could be used to do computation in principle. I couldn't work on that idea right away. And I started working when I read about subsequent developments. First, I read Feynman's paper in 1985.
Which one is that?
He wrote two papers on the connection between quantum mechanics and computation I forgot, in the early 80s, and the second was in 1985. I don't remember the titles of those papers, but in that second paper, he talked a bit about quantum circuits implicitly. He didn't have a definition of quantum circuits, but
he imagined what quantum circuits would be.
Right. He had some ideas how a quantum mechanical system could be used to compute. And still later, I learned some developments in quantum algorithms. And then the whole problem made sense to me. I mean, I knew how to make progress. And another thing that was helpful to make progress is that I studied some computational complexity theory. Because quantum computation is on the boundary between physics and computer science, and you also need to know the other side. You need to know about equivalences between computational models, because one puzzle was you could come up with various ways of using quantum mechanics. For example, one could try to create a quantum mechanical system and measure its energy levels with high precision. And that would be also something computational. And it's important to realize that you need to come up with one way of doing computation, and other ways can be reduced to it. So I got this idea and concrete examples from studying computational complexity. And by the time I started quantum computation, there was a circuit model of quantum computation, and it was clear how to simulate quantum systems using that model. Of course, at that time, formal results had not appeared yet about simulations. John Preskill did some work on doing simulations of field theory, but conceptually, the circuit model clearly allowed the simulation of some other things, and it felt like it was the right model.
Now, to be clear, all of the things that you're talking about now, you started thinking about this after your PhD, or even during graduate school, you were involved in this?
It was during my graduate school. I was just reading or learning occasionally some new things. And I actually started working on the subject after my PhD in 1985. I learned about Shor's algorithm, and I was told that Peter Shor found a solution to the discrete logarithm problem using a quantum computer. And I thought for a while and also found a solution.
Alexei, by this time in graduate school, how was your English? Are you reading papers in English? Were they translated in Russian? How did that work?
I read papers in English. My English was not very good, and I was trying to improve it. Actually, I was studying some English in grad school also, and that helped. But of course, the education was such that we were supposed to learn English and read papers as undergraduates. And I could read papers. I couldn't speak English very well as an undergrad. And during the grad school, I took additional classes to improve my English.
Now, of course, this is before the internet. How long did you have to wait until papers or journals made their way to the Soviet Union?
Some papers appeared in some libraries pretty quickly, but it still would take a month or so.
Is the process for defending a dissertation in the Soviet Union, is it more or less similar to the United States? There's a committee and you defend the dissertation?
Yes, you defend the dissertation. And I guess it's stricter than in the US. Because well, I don't know if it's strict or not, but it's also a committee. And at the Landau Institute, you need to present your work at a seminar before the dissertation. And then the dissertation is just a short thing. It's kind of formal because you give a very short presentation of several results. And there isn't actually time for people to follow and have a serious discussion during the dissertation. But The candidate is supposed to present the results before that at a regular seminar.
Now, this year you defended. This was 1989?
Yes, 1989.
And the big political changes that were happening at that point, the fall of the Berlin Wall, were you thinking about that and what it might mean for your career and opportunities?
Well, of course, I was thinking about that, but I didn't know how it was going to end up. It was exciting that people got more freedom. And of course, Berlin Wall is the Western perspective. We didn't think about Berlin Wall in the Soviet Union. What mattered is that people had more freedom, but early on it was also becoming clear that some bad changes were going to happen, and I didn't realize they would be so bad, because one thing I realized that inflation started, and it was difficult to save any money.
Now, Alexei, when you're talking about freedom earlier, are you referring to glasnost and perestroika?
Yeah.
Which, of course, is earlier than
say 1987. Perestroika started, and people received some political freedom. It became easier to travel, and actually, I took advantage of that. So I visited some countries. I think now I remember it a little bit better. As a graduate student, I made only one trip to Italy, to Trieste. And the other trip happened after I graduated, after I got my PhD. But still, it was the time where traveling became easier than before.
Alexei, I mentioned the Berlin Wall because, if I understand correctly, ironically, Mikhail Gorbachev instituted glasnost and perestroika in order to sustain the Soviet Union, to keep it together. And of course, that was the process that helped break it apart. I'm curious, after the fall of the Berlin Wall, if you felt like the Soviet Union was going to collapse, if that's where history was headed.
No, I didn't. I didn't have this sense, and I didn't think about foreign politics very much. Now people remember, people recall what happened, that Gorbachev gave up some something to the West. The influence of the Soviet Union over Eastern Europe. I didn't think about that. I was thinking about life in the Soviet Union, and the sense was that people can do more, but as I say, it's the feeling of something bad looming started with inflation, and eventually the situation became quite bad economically. And you may know that there was a big crisis starting 1990 and continuing for a decade at least. So,
Alexei, at least intellectually, after you defended the dissertation, were you thinking more about computation and quantum mechanics and that perhaps being the trajectory of your career? Or were you still focused on condensed matter theory as your academic specialty?
Uh, I was trying to just do something that interests me, and I still do the same now. I switched from subject to subject occasionally. Of course, I cannot switch very far, like to biology, but within physics.
And what opportunities, what professional opportunities did you have after you defended, particularly because this is right when the economic crisis starts to happen?
I was lucky that the director of the Landau Institute, Isaac Markovich Khalatnikov, arranged a program together with the Weizmann Institute, where scientists from the Landau Institute could visit. And I visited twice in 1991 and 1993, and worked for half a year each time at the Weizmann Institute, and that helped me financially. It was a very difficult time in Russia, and I continued working in this mode, having some long-term visits to foreign countries. The other country was France, and I also visited twice for a long time, working at IHES. So this way I could earn enough money for a living in Russia, because just staying at the Landau Institute and receiving the salary at the Landau Institute was not enough. There was one time, and I should acknowledge that I am grateful for this to the administration of the Landau Institute. They gave me a prize and raised my salary for a year substantially because of my work on quantum computation.
And what was your
my work in quantum?
What was your position at this point? Was it a postdoc essentially?
The system was and is different. There is no official postdoc position. Maybe now there is. I'm not sure. After my PhD, I was hired as a junior member of the Landau Institute. And that was a permanent job in the sense that there wasn't a fixed term, but there wasn't a legal protection either, like tenure in the US. It's just a job that is by default permanent. And people often stay for many years and got raises in salary. So there is no sharp distinction between the junior and more senior positions.
Alexei, tell me more about these international visits you were able to go on. For example, in France. Tell me more about that. What were you working on at that point?
In France, I was working on quantum chaos. At least it became as a work on quantum chaos. And I started doing that with Uzi Smilansky when visiting the Weizmann Institute. Quantum chaos could mean different things. At that time, the popular subject was the energy level statistics and how it's related to properties of classical trajectories. And this time, I would say quantum chaos is about out-of-time autocorrelators, because this way one can make a closer parallel with classical chaos. But anyway, I started working on quantum chaos in 1993, I think, together with Uzis Milansky. I realized that I wasn't making much progress on quantum chaos per se, but I could make some progress understanding some related mathematical problems, so-called dynamical Zeta function, which was invented by Ruel and studied by other people. There are several variants of this Zeta function, and showed that a particular variant is an analytic function.
What does that mean?
It's a function of a complex variable, and it's holomorphic in a certain disk that depends on the smoothness of the dynamical system. If the dynamical system is defined by smooth equations, then the analyticity extends to the whole plane. It's holomorphic in the complex plane. It's technical thing. So I was working on this sort of problems when visiting France the first time. And when visiting the second time, I don't remember very clearly, but I think by that time I had been working, I had switched to quantum computation, but I don't remember exactly.
Do you have a clear sense of when the term quantum computation or quantum computer started to be used, in the sense that we're doing science that might eventually lead to a quantum computer, not just a quantum computer as a theoretical concept?
Well, I'm not sure how I was thinking. I guess it was assumed that once we develop the theoretical concepts, the thing will be implemented, maybe not immediately. I don't remember.
Was the experience of traveling abroad, did that plant a seed in you to think that you might want to emigrate one day, to leave Russia?
I didn't want to immigrate until I realized that working at the Landau Institute was not great anymore, and I didn't have enough opportunity to discuss my work with other people at the Landau Institute, because I was the only person working on quantum computation. And also, as I say, the regular salary at the Landau Institute is not enough to normal life, not enough to support a family. So I would have to earn money somewhere else anyway. And these days, people have grants, Russian grants, or sometimes European grants. I am not sure how European grants work right now. Maybe due to the political situation, they don't work anymore. I don't know this, but at least this was the way for people to get money, sufficient money, and this is a lot of hassle applying for those grants. And maybe at the time I left, it wasn't even an option, because I left in 1998. Russia was very poor at that time, and I thought that wasn't even an option. The people were just poor in Russia, and that's it. and the only way to earn money was abroad. But of course, there were some professions where you could earn money in Russia, but they were not related to science. So I didn't want to immigrate until I realized that my prospect staying in Russia was not very good.
And so what context did you have? What availability did you have to establish connections to see if you could have an opportunity beyond Russia?
I wasn't actively seeking an opportunity to immigrate. And in the hindsight, it was smart because when I made this decision, I was already known as a physicist. So John Preskill invited me to visit Caltech in 19. I visited first both Caltech and IBM in 1997, and then I made a long-term visit to Caltech in 1998. And after during that visit, I decided to stay in the United States.
Now, what was that initial point of connection with John Preskill? Did he write to you? Did you get in touch with him?
Yeah, he wrote to me. Let's see. I'm trying to remember the sequence because we also met at a conference in Torino, a conference on quantum computation. And let's see. I think he first wrote to me, and I visited in 1997, and then came the conference where he made an offer to visit for a longer time. I'm not remembering very well.
Alexei, what were you working on specifically that caught John Preskill's attention at that point?
I was studying anyons and doing quantum computation by anyons.
And in what ways was that? I interviewed John Preskill, of course, and he told me in wonderful detail how important this was at the time. Looking back, how did that contribute to the questions John was considering at this point?
John studied anyons as a field theorist. And he had some papers about anyons and related objects in high dimensions. And I remember one paper was called Alice Strings and Cheshire Charge. And those papers studied anyons, possible anyons in high energy physics. And I think that I was the first to realize that anyons are connected to quantum computation.
What was that insight? How did you make that connection?
I knew something about anyons in the fractional quantum Hall effect, fractional quantum Hall systems. And as I say, I don't remember very many details of my past, but I do remember that studying fractional quantum Hall effect helped a lot. And it was see. Now, I came up with the idea of the toric code using fractional quantum Hall as an analogy. So my first thinking was to put a fractional quantum Hall system on a torus, and somehow I realized that the ground state would be degenerate and protected from errors if one puts the fractional quantum Hall system on a torus. I didn't know at the time, but the degeneracy had been already established by other people in this geometry. But the idea that it would be protected from errors was original, I think. I believe that people had not discussed that before.
Now, did you and John see this as complementary to what John was working on? Did it expand on his ideas? Did it move the field forward in a way that he was not doing? How did all of these things come together as an intellectual collaboration?
I'm not sure exactly. We had some discussions. You're asking about John's perspective. I cannot speak for him. But from my perspective, it was interesting that this concept that was born in high energy physics and condensed matter physics found an application, and it seemed very natural to me that anyons and topological states are useful for quantum computation because they offer protection from errors. And discussing with John, we talked about whether nature works in the same way. I recall that we had such a discussion, whether nature is fault tolerant. Yeah, but
when you first came to Caltech, was that as a visitor? Did John bring you out here to give a talk?
The first time, not exactly to give a talk, but just to visit for a month and have some discussions.
So a faculty appointment, that was premature at this point.
Right. So the first visit was for a month. The second visit was for 9 months. And after that, I went to Microsoft Research at Redmond and spent 2 years there. And then John was able to offer me a position, a research position at Caltech. Funded by his grant, but by IQI. It was called IQI at that time. And then a year later, I got the faculty position at Caltech.
What were your impressions of Caltech during that initial first month? What did you think of it?
It was very nice. It was nice discussing things with people because at the Landau Institute, I didn't have this opportunity. As I said, I was the only person working on quantum computing at the Landau Institute. So at Caltech, I could discuss this with John Praskal and with his students. I think Daniel Gottesman was there, and I was discussing quantum computation with him. But I don't remember whether it happened during my first 1 month visit or later. But that was fun too.
Now the timing is you were there for 1 month. And then you went back to Russia, and then you returned for 9 months?
Yeah.
Did John share with you his vision at that time of creating what would become the IQI, that he wanted to formalize this into a proper institute?
I don't remember. I don't remember.
And then what was your subsequent appointment? Were you for 9 months? Was that a visiting professor essentially?
Yes. It was both research position and I also gave some lectures on quantum computation.
Alexei, in what ways was being in that environment, not like at the Landau Institute where you were all by yourself, talking with John, talking with the graduate students and postdocs, how did that influence your thinking about quantum information at that point? What were some new ideas that you were getting exposed to?
New ideas in quantum computation.
Yeah.
I think it was on the technical level because I learned about other ways to do error correction. I had some scheme of doing error correction, and people here in particular, Daniel Gottesman, came up with other ways of doing error correction.
Now, did the opportunity at Microsoft, did that come together while you were a visitor at Caltech, or once again you went back to Russia and only then secured this position?
No. I went to, I did go to Russia, but I got this position while working at Caltech. And it happened like this. In addition to this 9 months offer from Caltech, I also got an invitation from Michael Friedman to visit Station Q. And I also talked with Michael, and that was fascinating in its own way because I learned some mathematics. I like mathematics.
What was the connection between you and Michael Friedman? Who introduced you?
Michael emailed me, and the reason he emailed because he had the idea of using topology in quantum computation, and then he learned about my work on anyons. And by the time I got the invitation, I think the paper had already appeared on the archive. And that's why Michael got interested in my work because it connected to his idea. I had a more concrete realization how to compute using topology, but the general idea was similar.
Alexei, tell me about Station Q. How well developed was it at that point?
Station Q had not started yet. It was Microsoft research at Redmond. And it was run by Jennifer Chase and Christian Borgs. So it was a group of mathematical physicists, basically, supported by Microsoft, who were doing the usual stuff. And Michael accepted this position coming from UC San Diego. But it was his dream to make something focused on quantum computation. And he founded Station Q a few years later.
What was the excitement at this point at a place like Microsoft? Was the vision that Microsoft really was going to create a quantum computer and that it would be useful for what Microsoft wanted to do in the future?
No, I think at that time, certainly before Station Q, it was just some abstract subject, and it wasn't the idea that we were doing something practical. Station Q was founded with the idea that a quantum computer will be built eventually. But at that time, in 1998, I think it was just a topic in mathematical physics.
Who else besides you and Michael? Who else was at Microsoft who were thinking about these things?
Who else? I mentioned Jennifer Chase, Christian Borgs, Latsalovas was working at Station Q at that time. And I'm bad at remembering names. I remember some people, but I forgot their names.
But it was a real research group. There were several people there.
Several people. It was a small group.
Now, did you stay connected to Caltech? Were you following the developments with the IQI?
I don't remember if I stayed really connected. I don't remember. I guess I stayed somewhat connected. Maybe I had some communication with John, but I don't remember.
Now, at this point, what is the work situation? Are you on a visa? Do you see this as a temporary opportunity and then you'll go back to Russia? Or did you see this as the start of making a new life for yourself in the United States?
I think I decided to stay in the United States during my first year at Caltech. So I wanted to stay in the United States because it was clearly a better environment than the Landau Institute at that time, at least for me.
And when you say the Landau Institute, I wonder if you can extrapolate to all of Russia. In other words, were there any programs in Russia that were focused on quantum information at this point?
I don't think so. But I should say that at the time I came to the Landau Institute in 1980s, it was one of the best places in the world for theoretical physics.
Right. Just not quantum information.
Well, quantum information didn't exist at the time, but
right.
There was a pretty sharp and unfortunate transition in early 1990s that led to this regression at the Landau Institute.
What were the topics that you were focused on during your time at Microsoft? What were the big ideas?
At Microsoft, I continued to think about anyons and topological quantum computation. We did some work with Michael Friedman and Wang and Larson on topological quantum computation.
And was this a temporary position, a staff position? Could you have stayed longer at Microsoft if you wanted to?
No, it was a temporary position for 2 years. They didn't offer me an extension. Later, I was offered a position at Station Q, but I decided to return to Caltech. I spent a year at Station Q.
What year was that?
Around 2005. I don't remember exactly.
Tell me about the process that got you back to Caltech.
After my first visit to Station Q, right?
Well, so you're at Microsoft for 2 years, and then you joined the faculty in 2002.
Yeah, and first I returned to Caltech in 2001 as a research scientist. And I'm grateful to John for offering me this position. It was funded by IQI. And then Caltech considered me as a faculty candidate and offered me a permanent position.
Now, I think, were you collaborating with John, for example, the paper Topological Quantum Memory came out in October 2001. Would this have been a collaboration with John and others while you were at Microsoft, or this would have been work when you were a research fellow at Caltech?
Topological quantum memory, I think it was while I was working at Station Q.
Uh-huh.
As I say, my memory is not very good. So, yeah, I think it was while I was still at Station Q.
And just a question on the nomenclature. That's a new term we haven't discussed. What does quantum memory mean? Topological quantum memory.
Topological quantum memory. First, quantum memory is a way to store quantum information, to store qubits. And to store them reliably, one needs some error correction. Topological quantum memory is a way to protect those qubits from errors using topological properties of physical systems. And in that particular paper, we discussed a surface code, which is not exactly a physical system. It can be realized using more conventional physical systems. But it's an error-correcting code, and we discussed error correction from the statistics of, from the perspective of statistical mechanics. We showed that the probability of an incorrectable error can be expressed as a StatMech problem. And we studied algorithms trying to correct errors.
Alexei, was this related at all to a similar project at that time you were working on, Wilson loop operators?
That was a different project with John Preskill. It also has connection with topology, but it's a different project.
In what ways? What was different about it?
Loop operators, this was John's idea, and I made some contribution to that work, but mainly it comes from John's original work on field theory. And he asked the question whether a Wilson loop operator can be measured quickly. And in that paper, we explored locality constraints on what can be measured quickly, because one cannot communicate faster than light. And one result was that a non-abelian Wilson loop cannot be measured quickly. One actually needs to go around this loop and collect information. And that was John's idea entirely. And I came up with a different thing about a billion Wilson loops that can be measured fast.
Fast relative to what? What does that mean, to be measured
Faster
fast?
than you don't have to actually go around, and if you calculate the time the light needs to travel around this loop, it's not the measurement time. It can be measured much faster. But some preparation is needed. There is a little bit of cheating. One needs to prepare for the measurement in advance, and then you can do it fast. Excuse me, I want to check my phone.
Sure.
Just a second. Oh, I apologize for that.
No worries.
I had to answer.
No worries. Alexei, just one last question for today. We're coming up on the end of our time together. When you returned to Caltech, this was during the transition period. You were there as a researcher as John Preskill was starting to think about the IQI. And then when you returned, the IQI was just getting started. It was already in existence. In what ways had quantum information grown institutionally at Caltech? In what ways were there more graduate students, more postdocs, a greater collaboration in working on all of these ideas?
I'm not sure how to answer this question. Quantitatively, certainly there were more people supported by IQI over time. And it was a bigger group, and John ran group meetings where the students would speak. At IQIM, actually, still as IQI, there was a regular seminar on quantum computation. So it was just a sufficiently big group of people to have a seminar. It was very good. But I cannot tell much because I kind of worked alone, or I collaborated with certain people, mostly with John. But somehow I don't talk very much with other people. Only when we work on a particular problem.
Right, of course. Well, Alexei, we'll pick up next time when you join the faculty proper in 2002.